and then from just a practical perspective of how do you use it? What does the program look like? And Science2Go is a program that provides students access to videos of real laboratory experiments and real laboratory phenomena. And then it pairs those with prompts that are meant to let kids evince their abilities to do science. So kids analyze data, they engage in argument from those data, they propose theoretical experiments, they refine the experiments we show them, all stuff in the service of precluding their science reasoning skills from stagnating if they are at home and can't do the stuff they would traditionally do in a lab. And I'm going to talk about how they can still use this in conjunction with the stuff you may be doing in the classroom. So I'm going to get to all that. The first thing I want to show you, and if you've been to some of my previous sessions, you will have seen this, but I find it fascinating. And this goes to the pedagogical philosophy here at Flinn Scientific, is we believe that it's very important to get your hands dirty when you're doing science. And that's something I think most science teachers intuitively believe. And if you look at the research, it's empirically supported. And I leave on screen here just an example of a fascinating study that was done at the University of Chicago, where researchers had two groups of students in a physics class. They had an action group and a control group. The action group was given access to physical manipulatives to study angular momentum and torque. The control group wasn't. They only had to study it from a hands-off perspective. And here's what the results are. So in a post-activity assessment, the students who had access to the manipulatives did much better than the students who didn't have access to the physical materials. What's more interesting is that the students who did have access to the hands-on materials, when the researchers questioned these students while they were in brain scans, they saw that sensory motor portions of those students' brains lit up on screen. So the research essentially said that kids who had touched this stuff before, their brains, when you ask them about those concepts afterwards, recruited parts of the brain that went unrecruited in students who didn't touch the stuff. So, the upshot of all this, the summary is here on screen, that these researchers posit that there is some underlying mechanism that is foundational to the value of physical experience. And so we really have to do this. And so the program I'm going to show you, students can do most of the experiments we show them with materials. In many cases, we hope that they'll have them in their kitchen, and I don't want to be too glib. I know that's not easy for everybody, but they're certainly easier to get than things like hot plates and burettes and that sort of thing. So I want to jump out and take you through Science2Go. So here's the program where we deploy these experiences with students.
Excuse me, Mike. I'm so sorry to interrupt you during your presentation, but I wanted to. There's the question here before you get too far down the line that talks about a journal that you reference. What is that journal, so that I can include it in the chat for people to pick up?
Sure. It is it's called Psychological Science. And it's, Google physical, I would Google the title and it'll probably pull up. I think this was open source, if I'm not mistaken, or it was on, I found it on the research group, but yeah, great article to read. And it'll actually link to a bunch of other articles you can see in the references that explore this topic empirically.
Awesome. Thank you so much.
Yeah, I mean, it's just a fascinating experiment too, because not everybody's got access to MRIs and can question students about physics while they're getting an MRI, but they had the resources at University of Chicago, apparently. So one other thing, so I said, how can students get their hands dirty before I show you the actual platform where this happens? This is one example of, we looked around our kitchen kind of in a MacGyver style and said, how can we ask students to do some high-level science with intermolecular forces? We thought, well, and this took a while, but let's get some M&Ms, dissolve up the food dyes in water, and do some chromatography. And so we dissolved up these M&Ms, the dyes in water, and under chromatography, we saw that we could get the dye molecules to separate based on their structures. And because they had different structures, they had different properties, and extending that further, they had different affinities for water and the stationary paper phase there. So this is one example. And if you pair this kind of activity with really intentionally designed prompts that are assessing students' ability to perform the 3 dimensions of something like the NGSS, content, science practices, and cross-cutting concepts, this is what we're trying to do here. So let me show you the platform. So if you want to get a better feel for what this is all about, you can go to Flinn, Science2Go.com, and you'll see, if I navigate down here, we have 6 different disciplines. We have 4 in high school and 2 in middle school. And what each of these are is a series of lab activities that students can do. Most of them they can do in their homes. But if they can't, we'll give them the data, disseminate the data through videos and through print media. So there's 10 labs in each of these bundles, the 6 bundles you see here. I want to show you what the experience looks like. So I'm going to log in. So if you're a teacher and you have an account, you would log in. And once you log in, you're going to go to your My Labs button and let this get called up. And I'm going to go to my Labs. And I'm going to show you an example of high school chemistry, because that's what I'm partial to, being a chemist. I wear that on my sleeve. So if we go into this, you'll see that this high school chemistry bundle has 10 labs. I'm going to go into lab content. And this is what all of these different lab bundles look like. So if you're in biology, if you're in physics, if you're in environmental science, you will navigate in and you will have your 10 experiences at the top of the page. And this will render on a phone, on a tablet, on a computer, what have you. And they're all the experiences follow a template, with the template being something that's designed to keep students active in the science practices. Now, I want to show you an example. I'm going to show you kinetics. Okay, so if you're a high school chemistry teacher, even a middle school chemistry teacher or physical science teacher, this is something that you could deploy to your students to keep their science reasoning skills kind of flexing, keep them active so that when they get back, if they're not in school right now, they're ready to kind of pick up where you left off and they don't lose that ability. So each of these activities starts with some guiding question, get kids focused. And the guiding question here is pretty straightforward. Why are some reactions fast, others are slow? It seeks to contextualize this for students. And then part of the secret sauce here are these videos where we show students videos of us performing these experiments in our lab. And I'm going to apologize here while I'm not going to show you this whole video, but I want to show you what happens here. So the videos will at some point ask a question. So in this case, we're going to ask students, think about how reaction concentration affects the decomposition of hydrogen peroxide. And most of us, are subject matter experts. So something like this we may know the answer to, but students will not have had experience with this for the most part. And so once students look at that question, we'll pause it on screen for a while. We're going to take them through the experiment. And we want to be really clear about how we do this. We want to hammer home the points of, if you're going to design a sound experiment, you have to have the appropriate control, independent and dependent variables. So we're going to show them in trial 1, we're going to do the reaction of 3% peroxide with sodium iodide and then soap. And then we're going to conduct that experiment and see how fast it goes. Okay, now once students watch this experiment, and this is fairly qualitative, but they will be able to see a difference, we're going to put them through a series of prompts. And these are things that if they're at home and don't have access to a lab, they're still engaging, their brains are still flexing and doing scientific practices, so to speak. So we may want them to make observations. And in our platform, they can type their answers directly into these text boxes, If you'd like, they can upload images. They can upload equations to support their answers. Now, these, as a teacher, you can change these prompts. If you don't like what we write here, I'm going to show you how you can edit this to, maybe you want your students to, can you draw a particle level diagram to show me why his reaction rate increases? You saw an increase in concentration. And so you can really change these to suit your needs. Students can save their work at any time and come back at any time. They don't have to do this in one sitting. So we make them go through this observe prompt, and then we're asking them some fairly high level stuff here. That's very much skewed towards science practices. This is less about demonstrating their content knowledge and more about, can students evince an ability to think scientifically, to at least engage in these practices in a theoretical way. And so here's an example. If you're a student, you've just seen that video where we vary the concentration of peroxide and see that as the concentration increases, the decomposition rate increases. We ask them to, what's a problem if you're going to do a similar experiment, but you change the concentration of peroxide and sodium iodide at the same time? And we want students to recognize, well, that's problematic because you have more than one independent variable. You got to control the sodium iodide if you want to measure the effect of peroxide concentration on reaction rate. It's kind of like one kind of silly analogy I always use is like, if I have a mouse in my house and I get a cat and put out mouse poison and the mouse dies, I don't know what to attribute it to. I don't know what's effective. Unless, and this is the silly thing I say, unless the mouse, shows up on your doorstep because the cat, is a gift. But I think these things are so important in an age where we're kind of overwhelmed with data and trying to sort fact from fiction. It's important to kind of inculcate in students the ability to really think about sound experimental design, sound data analysis. So we're trying to build that in them with these kind of experiences. And then we go on to refine, expand the experiment. Again, this prompt will repeat through all the activities. Here we're asking kids to, can you conduct the same experiment? And what changes would you make if you want to investigate temperature and reaction rate? And we'd want them to say, well, you would have to keep concentration constant, but in change temperature, and so on. And then we go to practice scientific reasoning. But you can get the sense that all of these prompts, again, they're not really asking kids to recapitulate a content fact. It's less about that and more about, let's keep you kind of thinking as if you were in a lab. You're not in a lab, but can we, intentionally kind of get you to engage with these prompts so that, when you go back to school, you haven't lost that ability, or at least it hasn't atrophied to some extent. And then we always want students to connect to their world. And some of these are probably more pertinent to some kids than others. But here is something in kinetics. We ask kids about rusting, and then we ask them to think about, what can car manufacturers do to slow down or avoid rusting? And students would say, having learned about collision theory, that, well, if we want to preclude iron from reacting with oxygen, we should coat it with something, or we should build our car from something that's not subject to oxidation. So things like this. Now, again, I said that if we always want students to get their hands dirty. So this particular experience, we use hydrogen peroxide. Excuse me here while if students don't have access to hydrogen peroxide, we always give them an at-home extension that they can do at home. And so what you're looking at here is an experiment in kinetics where we use just simple things, very simple, but it makes the point. And excuse me while I just, we use acetic acid or vinegar and baking soda. And what you're seeing on screen there is 2 glasses filled with a controlled amount of vinegar. And then in my little measuring cups, I'm going to add controlled amounts of baking soda. And students will see that the vinegar that hasn't been diluted with water reacts a lot faster with the baking soda than the vinegar that has been diluted with water. So undiluted vinegar, which is a higher concentration of acetic acid, reacts a lot faster with bicarbonate than the diluted acetic acid. So I got to stop myself from calling that acetic acid. But this is something, again, a fairly high level concept that if you look around your kitchen, you want to get really creative. It's kind of like an art form. It's kind of fun. I think about the show I watch, what's it called? Chopped, where the contestants are given a basket of foods and they're challenged to come up with the best dish. And this is what I treat this as. Like, can you look around your kitchen? And I want to teach kids about kinetics. What can I find? Or, if it's not in my kitchen, it's easier to get than copper chloride, let's say. So we always give those at-home extensions if kids can't do the actual activity. And then if you're going to be in school, we always provide a recommendation for a kit that lets students go a little deeper. So here we recommend, hey, pair this with Kinetics of crystal violet fading if you want your students to really get the hands-on experience if you have their time with them in school. Now, the other thing to point out, each of these, if kids absolutely want to, or if you want them to submit, and I apologize, this little bar on the left side of the screen, this is just a little fast search bar. So if I click one, it's going to run me all the way back up to the top here. So these students can also access these as PDFs, and I'm in a teacher view right now, but if you want to distribute the PDF versions of these to your students, you can click the PDF, and these are writable PDFs that include the same prompts that are in that digital system, and students can type their answers in here and submit to you that way if you'd like. The teacher version will have the idealized responses. And I say idealized because there's probably more than one answer for some of these. There's typically more than one experiment you can run in as you seek to answer a question. But in here, our idealized answers are in blue, so students can self-assess if they want, or they can do this in groups if they want, and again, just to keep active. We also, I failed to show you, for all these, we have gone out and we've included these learn more by exploring these links. And these are resources we've curated that are just open source from the internet that students can go to and explore a little deeper. This one is to a PhET resource, for example, a PhET simulation. But let me show you what it looks like to begin to change this experience to suit your particular needs. So let's say you don't like our prompts that we've included. I'm going to open up the S's in base one. And, I want to change, I'm a teacher and I want to change the prompts that Flinn has included. You can click customize and the system will ask you if you want to do that. And I'm going to just click, I'll give it some name that is germane to me, save. And then what the system will do is, notice in your teacher view will open up with these icons, these green icons. So this pencil icon, let's say I don't like this prompt here, I can click the pencil, and this opens up as a text box that I can change prompt here. Maybe I want a particle diagram, and I can save that, and that'll roll to students. This arrow here will let me upload videos. It'll let me upload data, links to external sources, whatever I want. So you can do this throughout, and then these new versions will roll out to students. And you can see here, in this experience, students are looking at the different color changes that these different salts lead to with an indicator, so acidity and basicity. And so that's that ability to customize, and then you can assign these out to students using this button. I want to give you a flavor, again, for what some of these activities look like. So if we go back to my labs, just to show you that, we do more than chemistry here. I'm going to go into the biology bundle and show you that if we look at the biology, it's really similar to chemistry. We have our 10 experiments or activities at the top. And if we, for example, look at cellular respiration, we're going to show kids how to build a respirometer. We're going to ask them questions that get at experimental design. Why is potassium hydroxide necessary as a control? And then we're going to show them we're going to show them how to measure cellular respiration rates using different materials. And in some cases, we will give them print data in here, but again, all the experiences are templated out to, let students engage in the science practices. So I think, some examples, and I've shared this in previous talks. I talked about I apologize while I share that. I talked about, doing intermolecular forces with paper towels. Here's another example where we do solutions by, in intermolecular forces by looking at a magic marker and how the green dye separates out into yellow and blue. Here's an experiment we did in our platform where we ask students to measure the heat capacities of quarters or some other object, and this is just a coffee mug. And a lot of these will ask students to, in those prompts you saw on screen, talk about, if you're going to identify an experimental design flaw, the big flaw here is this is not, the best system in the world. It's just a coffee mug with a meat thermometer sticking out of it, but it's the best we got in our house, and it actually works pretty good. But if we were going to do better, we would want something to be fully better insulated against heat transfer. So there's another example. Here's another one where we were looking at thermal conductivity with ice cubes, and you can see on the right, the copper pan is melting the ice cube a lot more efficiently than the paper. So we talked about thermal conductivity. And again, these are all paired with, these are at-home extensions that students can do. And if you pair them with the right prompts, kids are really, having to demonstrate high-level thinking skills. And then this is another one. I shared this with a gentleman in our last talk, where we're looking at the pressure that carbon dioxide molecules exert against soda can walls to keep it in tension. And it really goes to the power of gas particles to exert pressure. And once you open that can, this thing can collapse. So all of these activities we deploy as either the activities themselves or the at-home extensions that I showed you. So let me go back to my labs. I just want to show you an example from physics. And so here's our physics labs. We do a free fall lab where students can try to replicate Galileo's results by doing, and we think about Galileo didn't have fancy equipment, but if you measure a distance and try to measure the time it takes a ball to drop from that distance to the ground, can you experimentally determine G? And we give students data to do this. So some really neat things that they can do. And you, on the back end of this, you can assign grades to each of these prompts on a per student basis. You can leave students comments, really whatever you need to do. So this is what the system looks like. Now I'm gonna show you, and because I think we have time, I just want to show you an example of a video that we do in our acids and bases lab. And Vicky, can you tell me when I do this if the audio is okay, and if it's not, I'll do my best to kind of explain it after the fact, or you'll tell me if, Mike, it's really choppy and
sure thing.
Sure. So let me play this for you. So I'm about to play for you a video from our acids and base indicator lab, where students, let me just set the scene for you here. Students are going to be counseled on how to make an indicator from cabbage. They can do it in their house. We're going to show them how to do it, and they can use it to measure the pHs of materials in their house. So let me fast forward through. Well, no, I'll leave it like this. So you're going to see about 5 seconds of just opening screen, and then it'll get.
In this video, we're going to make our own indicator solution and then use it to test the pH of various household items. We start by chopping up a red cabbage. The cabbage is then boiled in water for 10 minutes. Finally, a colander is used to separate the cabbage pieces from our indicator solution. Here we have 3 different samples of our red cabbage indicator. The middle one is just the plain water. This is exactly what it looked like out of the pot. You can see it's blue in color. This one over here has had some acid added to it and has taken on a reddy pink color. And over on this side, we have a solution that we've added base to, and it's turned a shade of green. Here, we have 5 commonly found household items. In this container, we have stain and rust remover. Then we have baking soda, vinegar, glass cleaner, and finally, hand soap. Soon, I'll be adding some of our red cabbage indicator to each of these containers. But first, I want you to stop and make a prediction about what color you think each of them will turn.
So did that come through for you okay, Vicky?
It did, and I also queried our audience, and it came through for them as well, so all good.
Okay. I'm gonna, so this activity is, it's a new activity for us that is going to be released in our second round of chemistry labs at the end of November. Now, in this kind of round of activities, we take a predict and explain model. So you heard the presenter there say, predict what's going to happen. Now, what and again, I have some chemistry background, but one thing I like about this is this yellow one on the right here, that's a rust remover. So I would probably guess that that's probably acidic because acids tend to be good mineralizers. They tend to dissolve up stuff that doesn't want to be dissolved. So again, a student without a chemistry background might not get there, but just some neat things you can do. And then I want to show you, so you saw that video, I just want to show you how we communicate the results to students. And again, they don't have to measure the stuff that we measured in this video. They can go around their house and measure whatever. It's interesting though, like if we go back here, and apologize here for doing this so choppy, but the presenter told you that this red one was acidic and the one on the right here, this green, was more basic. But you do have to have some control to measure the colors that this indicator will change with the various household materials. So if I were a student and I wanted to know what the acidic one was, I would have to pick something from my cupboard that I knew to be acidic, maybe vitamin C, something else. So it's just interesting to think about how did we even do this? How did he even get this red thing? Because this is a Flinn scientist who's in California. We didn't give him hydrochloric acid. There's a guy named Alan. I'm guessing Alan probably took acetic acid or vinegar to do that, but who knows? But let me show you what the explain video looks like, and then we'll have time for some questions. So here's what we give the students after they make that prediction.
Let's now add our indicator to our different solutions. First, the stain and rust remover. This solution is acidic. Now we'll do the baking soda. No change is immediately obvious, but we'll come back and give it a stir to see if any color develops. Now for the vinegar. It's acidic. Don't worry about the color already in the glass cleaner, it won't affect the result. It's basic. And finally, the liquid hand soap. We'll put a couple of scoops in there and we'll give it a stir to make sure it all mixes through. Stirring the baking soda doesn't really make any difference. However, if we stir the liquid hand soap, the solution turns purple, which may be a little bit surprising. Soaps are usually basic. However, because skin is naturally slightly acidic, companies have started putting additives in to lower the pH. Here, you see a sample of the original indicator, so you can compare it to the other solutions. How did your predictions go?
Yeah, it's interesting. As I watched the video, I could, you could call Alan out for mixing the solution here with the solution here, but you also could be, you could be a little more magnanimous about it than I am. So these are some of the newer activities that you're going to see, but again, they're all going to deploy in that platform I showed you and be paired with these kind of prompts that students can enter directly into that you can change if you want. And they're things that students can do in their homes. And if they can't, the at-home extension is going to be something that they can do with materials that are, relatively accessible. So I think at this point, Vicki, if we have questions, you can take.
All right. I was having problems getting off the But I do have some questions, and thanks again, Mike. There was a lot of interest for this earlier this morning as well as today, and so we'll try to power through as many questions as we can in our remaining time. But the first question really relates to use by discipline. The district that this person is in uses integrated, not discipline specific curricula. How do Flynn's topics in Science2Go address that, and how do they address that for the middle school audience? Can you talk about that a little bit?
Yeah, I mean, that's a good question. I think we certainly, if we're in chemistry, for example, and we go back to something like, and if you want to talk about being interdisciplinary, apologize, let me log back in. And we're thinking about being interdisciplinary. What we'll often do is in a unit like reactions, when we ask students to connect to their world. Can you talk about reactions that you see all around you that are important to the sustaining of life? And that's a broad question, but for us to be interdisciplinary, we want kids to think about chemistry in the context of, let's say, biology. But we're not as interdisciplinary as, these are still, if you do the chemical bonds, you're going to learn a lot about chemical bonds. And it's not going to be, we're not going to bring in physics and biology as much as we could if we had more time than a 45-minute experience. But the interdisciplinary nature is going to come in. Let me go back in here. When we ask students to do this kind of experience, connect to your world, we're going to try to seek to get them to think outside of the particular discipline that they're confronted with in each activity. Now, if we go just from a pure so that's how we do that. From a pure topic level, if you go into middle school, there's two middle school bundles. And I'm going to show you in the physical science, we have 10 topics. So students, if they engage in any of these topics, we are going to do a good job, I think, of connecting them to things in the student's world. But yeah, we may not be able to link heat transfer to biology and to physics. So I guess the way I would tackle that is you'd probably want to have more bundles than less, and try to give students exposure to activities in the physical sciences and the life sciences. When they're in any particular activity, we're going to try to get them to think in a little interdisciplinary perspective by asking them to connect to their world. And that's how we do that. But it's, we recognize that in 45 minutes, it's tough to do that as completely as we would like to. And we have other programs for doing that.
Great. Okay. Thank you, Mike. Appreciate that response. I had a question about simulations. Do you have any ideas, or is there any coverage within Science2Go with lab simulations, specifically those that would allow students to take quantitative data? And again, looking at something that is aimed at the middle school level.
Yeah, like here's some of these do have simulations we built if we feel like that's really going to add a lot of pedagogical value. So for example, here's an acids and base one, and this is one we also, we change it and we deploy it at the middle school level. But here's an example of a simulation that we would build to go with this. And about 30% of these have these simulations. But if I click this, and this is a Flinn simulation, whoops, no, I'm in the wrong one. Sorry. Let me go back. Billion windows open. So we will have them collect data. Let me show you here. I'm sorry, give me 1 second here, Vicky.
Sure, no problem. And ladies and gentlemen, while Mike is looking for the particular window, just wanted to let you know that a little while ago, I put in a link for a survey, NSTA make sure that both they and we are giving you what you need during these types of gatherings. So I'm going to actually put it into the chat again so that you don't have to scroll up and down looking for it. But if you have an opportunity either at the end of this time during your virtual conference experience to complete that, we'd certainly appreciate it.
So
Thank
Vicky,
you.
so here's an example, and this actually, as I think about it now, goes to the how you can make this a little more interdisciplinary than maybe it exists in its kind of canned form. But this is a simulation that we pair with the atomic structure lab in chemistry, and we pair it with a similar experience in the middle school level. If I'm a student, I go here, and you don't have to have a high level science background to understand what's going on here. This is basically an exercise in fingerprinting. These are spectrum tubes. Each of these contains a gas represented by the elemental symbol here. And what you're trying to get a feel for is what that element's atomic spectra looks like. And every element has a characteristic atomic spectra. And this is how people can understand the composition of stars, for example. But if I'm a student and I want to play with this in a qualitative sense, I can put one of my spectrum tubes in this power supply, turn it on. I actually have to turn it on. And then you can see it's glowing there, and I click the spectroscope and I'm shown the atomic spectra for this particular element. Now, if I do that and compare this, all of these known spectrum tubes, hydrogen, helium, nitrogen, oxygen, mercury, to the unknown, I can get a feel for what the unknown is. And so this is a way that we try to build some data analysis. It's not quantitative, but it's, again, we go to the point that this is how people kind of do things in astronomy. And so this is a way that we build some interdisciplinarianism into the activities. So we have a number of these things. Another example, I was trying to show you the acids and bases one in there. We have kids manipulate acids and base indicators like thymol, blue like phenolphthalein, and then they just drop various solutions into the indicators and record the pH is based on color change. So these are a couple examples, but there's no, in our videos, you can't actually like, put a little measurement tool in there and record the data. So ours tend to be, if we're going to give you quantitative data, we give that to you in the activity. It's as HTML text and it's in a table or something like that.
Gotcha. So the making sure I was unmuted. So the flexibility is there with regard to being able to
Yeah, sorry, you broke up there a little bit, Vicky.
Oh, sorry about that. No, just confirming I understood that basically there's a lot of flexibility within these labs for teachers being able to come in and make edits and changes based on understanding their students and where they are.
It depends on the lab. It's kind of to each. What do we think the best way to get the lab across is, and the way that's going to let students do it at their home and at the same time flex their scientific reasoning skills. Like, so for example, if I go back to the physics bundle, the free fall lab, this is something that we ask students to do. Can you replicate Galileo's results? Can you come up with an experimental value for the acceleration due to gravity? Can you design an experiment to do that? Probe the faults of the experiment, probe sources of error. And here students can really get a sense, well, yeah, if I drop a small sphere and know the distance it drops and I time it, I can come up with an experimental G, but I really should do a lot of trials and not just depend on a single trial to come up with that G. And if I want to get really crazy, I should do standard deviation and that sort of thing. But here kids can even prove that, yeah, objects, do fall at some universal constant that we can attribute to gravity. So it depends on the lab, Vicky. In some cases, if we go back to the kinetics lab we saw, that's a little bit more qualitative, where students are observing the change in reaction rate owing to concentration. So it's kind of a bi-topic approach, I would say.
Got it. Okay. All righty. Well, we have come to the end of this presentation, and I just want to leave the audience with a couple of housekeeping details. You may have come into this workshop after we began and missed the opportunity to be included in a door prize drawing. We're going to do that post-conference, so I need to make sure that I have a first and last name, an email, and the state that you are joining us from. You can do that to me privately so that it doesn't come into the public chat. And my name is Vicky, so you should see that in your participants field. So that's one. The second thing is that NSTA, again, has given us a survey for you to complete just to let us know how we're doing. So please be sure to access that link before we conclude here so that we can get that information. And then if you have additional questions about Science2Go, you're looking to understand how it works from a licensing perspective, how it fits into your classroom, and how you can get started. If you would go to our marketplace, the Flinn Scientific Marketplace, and I'll make sure that that URL that's right here in the NSTA Engage conference, then you can click on the information, the button that says, please send more information, and that will signal us to have an account exec and answer those very technical questions for you that you would need to begin your Science2Go experience, including being able to get set up in a trial if that's something that you're looking for. If you don't want to go over to the marketplace and click that, you are more than welcome to, in the chat field, just say, send me more information, and I can get you connected with the account representative or content person that can give you more information. All right, I think I've come to the end. We've got about 90 seconds to spare. So Mike Marvel, I just want to thank you for your information and for your time and for introducing us to this great content in a package that's really important for these days and times. And ladies and gentlemen on the line, we really value your time. We know that you've got many choices here and a lot of fish to fry, as it were, as you're navigating your way through this conference. So we appreciate you spending this 45 minutes with us. So I'm Vicky Myers with Flinn Scientific. Thank you so much for joining us, and enjoy the rest of Engage 20.